Welcome to the Cosmic Pie Podcast. I'm your host, Wayne Barkhouse, and here with me,
Robert Moore.
So this is Season 2, Episode 19. We do have a live chat feature that's running, so if you have any questions or comments that you like to make throughout the podcast, please feel free to use that feature. We are broadcasting live from the campus of the University of North Dakota.
Yep, and wonderful state of North Dakota, right next to Minnesota, but you know.
And Robert, of course, you might notice that I have a new microphone.
You do, yeah.
Last week wasn't too pretty in terms of the audio quality out of my mic.
Hopefully we've got this figured out. We still learning a little bit here, folks. So
We're not in like the optimal room that we'd like to be in either.
no, we're not.
So because of that, we get a lot of echoing that we have to try to control the best that we can.
Yep, and hopefully we've done it.
Now, as a disclaimer.
Disclaimer. Oh yeah,
You
disclaimer.
say it?
I guess so. The views expressed herein are those of myself and Wayne. They are not the views necessarily of the University of North Dakota or the Department of Physics and Astrophysics or anybody else. So, just us.
We're the ones to blame, right?
We're the ones to blame. The buck stops with us.
Okay. So, Robert, it is September the 17th. And it's 5 p.m. essentially Central Daylight Time. And coming up in a few hours, we have a celestial event.
Woohoo!
You want to tell people what this is all about?
All right. The celestial event is a annular, I think that's the term still. Or no, a partial.
There we
Partial.
go.
That's the word. I'm having trouble with words today.
That's like a half a week, isn't it?
Yeah, partial lunar eclipse.
That's a toupee.
Yeah. Toupee or not toupee?
So it'd be like the moon gets a toupee tonight for a period of time, right?
Yep, just for a little bit.
Now, the times, if you want to go to our first slide, Robert, we can kind of show people what it's all about here.
There we go.
So tonight, at least at 9:12 our time, like I said, Central Daylight Time,
Yep.
Part of the moon will enter the darkest part of the Earth's shadow.
And the rest of it will be in the light part, the penumbra.
Right. So just a small part of the moon, a small fraction of the moon will look dark.
Mm-hmm.
And normally it should be a full moon. It is full moon phase, and it always occurs, of course, whenever we have a lunar eclipse, because the moon, Earth, and sun make a nice line.
Right.
But in this case, what's happening is that part of the moon will enter the darkest part of the Earth's shadow, and that'll last for a little over an hour. So that'll go from 9:12 to about 10:17 tonight. Mm-hmm. So hopefully the weather cooperates. You hear that knock, Robert?
I hear that knock. It's supposed to be pretty good here.
Yeah.
You know, we can't say where you're going to be located, but the weather should be favorable for North Dakota and western Minnesota.
I think later tonight we are getting more clouds coming in, but
Yeah.
hopefully that won't happen until after this event is over.
Indeed.
And the other good thing is notice the time. A lot of these, did you ever notice that anytime there's like astronomical events happening, and I'll show you an example of it later, but they happen like at 3 in the morning or 4 in the morning. Did you notice that?
Yeah, I do notice that, yes.
And it's always on a night where you have to get up early next morning to go teach or something like that. Right? So you walk the clouds with your eyes hanging down to your kneecaps, you know.
Yeah.
You know, that sort of thing. So this happily is happening early enough that most people are normally awake at this time anyways.
Right.
And the other thing about lunar eclipses, this is a partial one, so it's not like the whole moon enters the darkest part of the Earth's shadow. Good thing about lunar eclipses is that as long as you're on the night side of the Earth, you can see this event.
Yes, I was going to mention that, so thank you for bringing it up.
So unlike solar eclipses,
where you've got to be in a narrow band of the path.
In that case, it's the moon shadow that hits the surface of the Earth. And because the Earth rotates as well as the moon's going around the Earth, that spot turns into a track, as we would say, a path of totality. You have to be in that path if you want to see a total eclipse of the sun. And so most people, if you don't journey anywhere chasing these things, and there are eclipse chasers.
There are eclipse chasers.
And
I chased this last one.
In fact, these are usually older people with lots of money.
Yes.
Because a lot of times these eclipses are happening in, you know, to us, exotic places on the Earth like Australia or Spain.
Or South Africa or Antarctica or, yeah.
And you try to go in Australia, you know how much money that costs?
I have not looked that one up. I have no desire to go to Australia. Everything's trying to kill you there.
Be ready to open up that big wallet I see there on the back of your pants there, and that's what you got there.
Yeah.
It's either a notebook or a big wallet. What you know?
It's actually a phone.
But yes, it costs a lot of money to go to these places. So if you don't go anywhere because you can't afford it, you're not going to have very good odds of seeing a total solar eclipse in your lifetime. That's how rare they are at a given location.
At a given location.
Yeah.
They're not really that rare. Just at any given location, they're going to be very rare.
In the last couple of years, last few years, we've had 2 solar eclipses whose path of totality went through the United States.
Right.
But they didn't go through Grand Forks. So if you stayed here, you've seen a partial solar eclipse. So you had to do some traveling.
That's it. And travel we did.
We did. So, so tonight that should be an interesting event. And hopefully wherever you're located, hopefully, number one, you listen to this podcast before it happens.
Right.
Because if you wait 3 days to listen, you're 3 days late.
Right.
And the other thing is, hopefully you have good weather wherever you are.
I'm hoping for clear skies across the United States. Let's let people see this one. So
now, there's also another event that's occurring. Actually, we should talk about a little bit more.
We should talk about why lunar eclipses aren't every full moon.
So, Robert.
Yeah.
What is the phase of the moon during a lunar eclipse?
During a lunar eclipse, it's full moon all the time, every time.
In order to have a full moon, that means that sunlight must reflect off the near side of the moon. That's the side that faces us.
Right.
And reflect back towards the earth, at least some of the light that we can see, right? Mm-hmm. Okay. So for that to happen, then, the sun, earth, and moon must form a line.
There you go.
But if that's the case, then, Robert, why doesn't the moon enter the earth's shadow every time there is a full moon?
And that's because the plane of Earth's equator, the ecliptic, does not match up with the plane of the moon's orbit around Earth. So, kind of like this is showing, there's a 5-degree offset. So the moon may be as much as 5 degrees out of the Earth's shadow.
Either way, up or down, right?
Up or down.
Now, what is the apparent size of the moon as viewed from the Earth?
It's about half a degree.
So you can take 10 full moons above the Earth's shadow or 10 full moons below the Earth's shadow.
Right.
So anytime there's like a random full moon occurring, chances are the moon's either going to be above or below the Earth's shadow, and therefore we will not have a lunar
eclipse. And this is why solar eclipses are not, they're about as common and frequent as a lunar eclipse, but it's somewhere. You know, the moon is much smaller than the sun, really, so its shadow is much smaller than the Earth. So
what's the phase of the moon then, Robert, when there's a solar eclipse?
That would be a new moon.
Right. So you want to be able to form a line from the sun to the moon to the earth, a nice straight line, because you're in the shadow of the moon. And we would not see light reflected off the near side of the moon and that position that the moon is in its orbit around the earth when it's that new moon phase.
Right.
And so normally you would not be able to see the moon. But of course, if it's blocking the sun,
you're not going to see much anyway because the corona is still there, which is still bright and enough glare to keep the moon from being visible. So,
well, you can definitely tell where the moon is.
But you can tell where it is because it's a black disk that goes across the face of the sun.
And because of that 5-degree offset, then normally the moon would be
above
or below, which means the shadow of the moon does not cast on the surface of the earth when it's that new moon phase.
There we go.
So same kind of thing.
So it's the same kind of thing. And, you know, again, the reason why a solar eclipse is only visible in certain locations on Earth, whereas a lunar eclipse is visible from the whole night side, the moon's shadow is quite a bit smaller than Earth's shadow. So
right. So that would mean that on average, because you only have to be on the night side of the Earth during a lunar eclipse compared to being that very special path of totality during a solar eclipse, that way more people
see lunar
eclipses compared to solar eclipses.
Yeah, and they seem more frequent, but yeah. So
now the other interesting factoid in all of this is that the moon does not maintain a constant distance from the Earth.
Oh,
and I'm
that's
not talking. And I'm not. Well, let's look at it 2 different ways.
Yeah.
Because I think some of the media hype tonight is it's a super moon,
right?
And it's also going to be that partial lunar eclipse.
Right.
So do you want to explain to people what do we mean by supermoon?
Okay. So the moon's orbit around Earth is not a true circle. It is an ellipse, kind of like Earth's orbit around the sun is an ellipse. So there are times when the moon is going to be closer to Earth, times where it's going to be further away from Earth. Now, the difference in this size between close and far away is only about 17%. But the supermoon refers to the fact that the full moon is going to happen at that time of closest approach to Earth for the moon. And so it is larger than when it's far away, when you have a full moon at the far away point. So that's what's meant by a supermoon, and it just means that the moon's a little brighter, a little closer, looks a little larger, and it's a small amount.
Yes, because some people, you get the impression, if you're not familiar with these terms, that somehow tonight the moon's going to fill up half the sky or something.
Right. And there are people who believe that, and it's like, no, the moon will never fill up. Since about the past 3.5 billion years, the moon has not filled up the night sky.
Well, here's the other thing you can do as an experiment. Anyone can do it. Doesn't cost anything. Is that some people, you get the impression, not some people, everyone gets the impression, I do myself, is when you go and you look, let's say the moon rises. It's rising in the east, right?
Right.
It looks really large when it's near the horizon.
It does.
That's an optical illusion.
It is.
And one way you can get to test that is actually put out your thumb, let's say, to cover the moon when it's higher up in the sky.
Right.
And then try the same experiment when it's really close to the horizon to see if it is significantly larger than when it was much higher up in the sky.
And quick quiz, our answer to the quiz here, it's the same size.
It's the same size, yeah. So that really tells you your senses. You can't trust them.
You can't trust them at all. Yeah.
And
there are so many things that, we trust them. We put trust in eyewitness testimony. We put trust in all these different things. And it's like, no, your senses can be tricked so easily. It's not even funny.
And when the moon is near the horizon, you have the landmarks around you.
Trees and hills and so forth.
That give you this impression that the moon is really big, for some reason. But that is not the case. And like I said, you can just put out your thumb or something else to measure the diameter when it's not near the horizon and then compare it to when it is. And you'll see it's the same.
It's the same.
Now, the other interesting thing is that the moon, as I mentioned before, is moving away from the Earth. But it's not just the fact that the moon orbits in an ellipse around the Earth.
Right.
But we have measured the moon to be slowly drifting away.
3 centimeters per year.
Yeah, so about an inch a year, roughly. And we get those numbers not by making them up.
Right.
But by bouncing lasers off the surface of the moon. In fact, during the Apollo program, astronauts went to the moon, and one of the things they left behind was laser reflectors.
Right.
So that we could take our laser here on Earth and bounce them off the surface of the moon much easier than just the random dirt that gets scattered in various directions.
Right.
And so the return signal is much weaker. If you actually have a reflector, right, it's much stronger, and you can get a much better measurement and less of an uncertainty in the value of the distance.
But how do we know that it's the light bouncing back from that laser? How do you know that it's the laser light, not just light in general, bouncing back?
Yeah, so 2 things. The laser, we know the wavelength of it.
Right.
And so we have that. And the other thing is we only shine them at certain times on the moon when we're ready to make a measurement. So if you only see it every time you turn your laser on, it's like you're in a dark room, and the only time you see a flashlight is when you turn your own flashlight on. It probably tells you it's your flashlight that's illuminating the dark room, you see?
Yeah. So we have reasons why we say these things. It's because we have made measurements of it.
Now, why this is interesting is because as the moon moves further and further and further away, it gets smaller in apparent size.
Right.
So there will come a point in time. Oh, yes, it's millions of years from now. We won't see it unless somehow you can go in hibernation for a long period of time. There'll be a time in the distant future where the moon is so far away from the Earth that it will not be able to cover completely the surface of the sun.
Right.
And therefore, we will never, ever have another total eclipse of the sun. We'll always see a thin ring around the moon, which is the surface of the sun, and that ring will just get wider as the moon goes further away.
Yep.
So that's millions of years from now. We
That's
don't have to
million, yeah.
worry about it.
We don't have to worry.
So,
Well, y'all don't have to worry about it. I intend to live forever.
Well,
It's the
thankfully,
last thing I do.
thankfully, we live in an era where we don't have to worry about that. The moon is able to cover completely
Yep.
the surface of the sun, at least the photosphere, right, which is the visible surface that we see with our eyes when we
Right.
look up at the sun in the daytime. But things, just because they're the way they are today, over long enough time periods, things do change. I mean, you just got to think about geology.
Mm-hmm.
You build your fine cabin on some mountain range in the Rocky Mountains. 200 million years from now, your distant relatives are not going to be using that same cabin, even if you made it out of titanium or something, right?
Right.
Because the Rocky Mountains themselves are changing.
Yep. I mean, just look at all the landslides and mudslides and things like that. I mean, the Earth is changing. It just takes a long time for it to be a significant change.
Well, just look around us where we live here in Grand Forks.
Right.
In the soil, the black clay. I mean, that was at the bottom of the great red, what would you call it, lake or something, or ocean?
Something like that. It was
At
at the bottom of a shallow sea.
An inland
Yeah.
sea. So that's where that's the sediments, right? That all piled up at the bottom of the sea. And so things do change, right? They're not going to be the same, millions and tens and hundreds of millions of years from now as you see around us today.
Right.
So
So
Now-
we have another event coming
another
up.
event that's coming up, but this one is a little bit later on. So it's next week on September the 22nd. And this, of course, happens early in the morning
5:41 a.m.
or,
I think
or
I'm
late
on
at night, depending on how you arrange your sleep schedule.
that. I might get up for that because I normally get up at about 6 a.m. anyway. So
Yeah, well, this is a perfect time. The only thing you have to worry about, of course, is the
city lights.
the weather. I was
Or the
thinking,
weather.
right? 'Cause, it's a rule of thumb. Usually, it's like a telescope, right? You get a telescope for Christmas as a young child. You're almost guaranteed that starting on Christmas Day that evening, it's going to be cloudy for the next 2 weeks.
Yes.
Just the torture of wanting to use your telescope and the weather not cooperating.
Right.
And so when you have things that occur in the sky, like eclipses or whatever, a lot of times, the weather does not cooperate. And there's some rule of nature about this,
Yep.
that you're trying to make
It seems that way for sure. Yeah.
Anyways, but this event, what's happening here is that the moon will move in front of the star cluster, the Pleiades, or the Pleiades, or the Seven Sisters, or the Plough, or what other name you might have for it, depending on where you live in the world.
Yep. It is not the Little Dipper, though.
It looks like a little dipper.
It looks like a Little Dipper, but the Little Dipper is only little in comparison to the Big Dipper.
Right. So the moon then will cover a part of the cluster because there's so much of it, it can't cover it all. It's larger than a half a degree in size,
Right.
apparent size. So it will cover that in the early morning of September the 22nd, at least from Grand Forks. So this is, if you like, a snapshot of the screen from Stellarium, showing you what the view would be here at 5:41 a.m. Central Daylight Time on September the 22nd. Now, this cluster, according to the latest, greatest data we have on the distance to this object, which comes from the Gaia mission, which is a European Space Agency, an ESA mission, that's making very detailed measurements of the proper motion, that is the motion of stars through space, and also their distances, which is the really interesting thing, using what we call parallax. So, Robert, would you like to explain a little bit what parallax is all about, and maybe some easy demo that somebody could do to get the idea about it?
Sure. Parallax is essentially the apparent shift in position of a nearby object against a background further away. And an easy way of doing it is to look at your thumb, hold your thumb out at arm's length, close one eye and look at it, and against that background that's far away, so some trees or something that are a good distance away from you. Close one eye, note the position, then close the other eye, and you will see it shift position because it's close enough that the difference in position of your eye will allow it to seem to shift.
Right. So for the Earth, if you're on the Earth standing making observations, especially if you have a telescope in space, let's say orbiting the Earth, you don't have to worry about the blurring effect of the Earth's atmosphere. So you could look at some nearby star on one side of the Earth's orbit, let's say, I don't know, January, and then wait till July and measure the relative position of that same star relative to background stars and note the shift in position. And that would indicate the distance to that object because it's related to how far apart your measurements are taken from each other, the baseline, which would be the diameter of Earth's orbit,
Right.
which is about 2 astronomical units, as we'd say.
Mm-hmm.
And also how far away is that nearby star from the center of that baseline, which would be the position of the sun in that case.
Right.
The further an object is, the smaller that angle. In fact, we talked about this recently in my introductory astronomy class. When you look at ancient astronomy and what astronomers knew back then, all the way up into modern times, the two competing models, especially, let's say 2,000 years ago, the geocentric model was the dominant model that explained the solar system. And then later on, there was Aristarchus in the early ancient Greek times, but Copernicus reinvented, in some sense, the heliocentric model, the sun-centered model. But the geocentric model was around for well over 1,000 years before Copernicus. In fact, you can think of every generation of children I went to school and learned about the geocentric model. And then along comes somebody that says that's totally wrong, this is the better way of looking at it. There's got to be some huge motivation to allow you to do this, quote, paradigm shift in our understanding of the true nature of the heavens.
Right.
And one of the things you could argue is, well, wait a minute. Number one, if the geocentric model is correct, that says that the Earth is at rest and everything goes around the Earth.
Mm-hmm.
And that's a natural type of feeling you get because, once again, your senses tell you there's no motion. I don't feel the Earth rotating. I don't feel it moving around the sun. It's not like when I'm walking down the road, I'm swinging back and forth because of the motion of the Earth. So none of my senses tell me that the Earth moves. But when I look up in the heavens, I see things moving. I see the sun rising in the east, setting in the west. I see stars moving across the sky at night, all of these things. And the other thing I could say to somebody who's trying to convince me that it's the sun that is the center of the solar system and that the Earth goes around the sun is, well, if that's the case, if the Earth does move, then I should see the parallax shift. I should see the shifting of these nearby stars relative to more distant stars. In fact, Galileo,
Right.
very famous scientist, Galileo, in the 1600s, used a telescope and he looked at Mizar and Alcor in the Big Dipper, Ursa Major, and looked for a shift in position as the Earth went around the sun, and he didn't see it. And so he took those observations like a bad scientist and hid them.
Right.
They were only found later after he passed away and people went through his papers. So you don't do that in science, of course, right? You publish everything, whether it's a negative or a positive, depending on what things you're trying to look at. You never hide any of that data, right?
Right.
I mean,
You're not supposed to. That's for sure.
that's essentially fraud.
Uh-huh.
And that has happened. You think of medical science where people have fake data or hidden things trying to get different, things passed like vaccines or treatments and stuff. And
Yes.
that could make the difference between millions of dollars in grant money and no money, right?
Right.
So that's a big, big deal. But anyways, we don't see the shift. In fact, it wasn't until the 1800s, right around 1836 or so, that Bessel, the mathematician, used a telescope and he actually observed parallax for the very first time. Nobody had seen it prior to that.
Right.
But nowadays we have telescopes, especially in space, that can easily see this motion.
Right.
And that proves, in case you're doubting, that the Earth does indeed move.
Yep. And people go, well, why haven't we seen it before? And the answer is because we really underestimated, or the ancients really underestimated just how far away stars are. And so even the closest star has a parallax angle of much less than 1 degree. So the angles involved, that apparent shift in position is really tiny.
Okay, Robert, now I'm going to bring up my nerdness.
Okay.
You ready?
Ready?
The star with the largest stellar parallax is the nearest star to the sun, right? Proxima Centauri.
Yeah.
It has a parallax of 0.77 arc seconds.
Right.
Less than an arc second.
Less than an arc second. And again, for people listening in, an arc second is 1/3600th of a degree. So there's 3,600 arc seconds in 1 degree. And a degree, think about your old work with a protractor. 1 degree is one of those marks, the distance between one of those marks and a protractor. It's a tiny unit already. And then you're going to divide it up 3,600 times.
Now, the spacecraft currently that's making these observations of stellar parallax, the Gaia mission, it's released their data in sort of chunks, if you like, right? So there's like a core dump of the data release 1, then data release 2, then the current one is data release 3. And based on data release 3, which should be the best data and with the smallest uncertainty in the measurements, you can see the distance to the Pleiades. It's 135.74 plus or minus 0.10 parsecs.
And what's a parsec?
Well, let's wait.
Okay.
If you translate that into light years, it's 442.72 plus or minus 0.33 light years. Now, a light year is probably easier to describe to people than a parsec.
Right.
So a light year is the distance that light travels in 1 year. So it's roughly about 9 trillion kilometers and about 6.5 trillion miles.
Right.
So you think of light traveling at roughly 300,000 kilometers per second. You can get to the moon in 1 second. You can get to the sun in just over 8 minutes. You can get to the outer solar system in about 5 hours or so. You can get to the nearest star to the sun in a little over 4 years. You can get to the center of the Milky Way in 26,000 years. You can get to the nearest galaxy to us that's like our own, a massive spiral galaxy, the Andromeda galaxy, and 2.5 million years. And you can get to the other side of the observable universe in less than 14 billion years.
Woo-hoo.
Now, using that unit of distance,
right,
okay, the Pleiades is over 442 light years away. So when you look at the light coming from that object tonight, which you can do, you can see with the unaided eye, you don't need telescopes, you don't need binoculars. That light left that cluster of stars long, long before you were born. In fact, it's back in the time of essentially Galileo, right?
Yep.
The 1600s. And it's been on the journey ever since.
It's trying to wrap your head around the scale of these things it's one of the hardest things to do. The scale is just enormous.
Well, it's like, when you learn physics in maybe, I don't know, elementary, let's say kindergarten, right? And a teacher holds up a little piece of wire, right, that's several centimeters long and say, what does this represent? And it's the distance that light travels in 1 nanosecond,
right?
1/1000th of a second. And you think, oh my God, that is so fast. How do people even measure that? That kind of thing. And then you think about it, it's like, oh, I can go around the earth, or somehow I could go in a circle, the circumference of the earth, I can go around in 1 second 7.5 times. I mean, imagine going from one place to another. You can't do it because you can't slow down, The speeding up and slowing down would be by far the vast majority of the time.
You'd vaporize the earth with the amount of energy you'd have to bleed off.
So you think that's so fast, right? And then you get the sense of scale. I can get to the moon in about a second. Oh, wow. It takes days to do that in an ordinary spacecraft, right? I can get there in a second. But then someone says, the center of that galaxy that you can barely see with your eye in a dark location, the Andromeda galaxy, the light that enters your eye tonight, which is the furthest object you can see with the unaided eye, Trivial Pursuit question.
Right.
That light has been on its way for 2.5 million years. It took that long for light to get here, traveling at that fantastic speed.
Yep.
And that's a nearby galaxy in our backyard.
Right.
So the size of the universe, should I dare say it,
is immense.
It's astronomical.
It's astronomical. or should we say it's governmental? That's another matter.
That's the national debt.
That's the national debt. Yeah. All right.
But you didn't explain now what a parsec is. You want to?
So I get to explain.
If you want.
Okay. A parsec is simply the distance at which that parallax from one side of Earth's orbit to the other is 1 arc second.
Cut in half.
Right, cut in half.
Yeah, so it's half of that. So it forms a right triangle.
So it forms, yeah. So, 1 parsec is still a very great distance.
3.26 light years.
Right. Holy cow.
So that means the nearest star to our sun, Proxima Centauri, is just a little over 1 parsec away.
Mm-hmm.
That's what that means, because it's about 4.2 light years away.
That's it.
So that's a sense of scale. And the reason why astronomers use that number, because it's an observable number.
Right. Yeah, I mean, when you look through a telescope, all you're really seeing is angles because it's a sphere, it's curved. So you're seeing angles, and that's what you're really measuring. You think you're measuring a distance, a length, but it's an angle.
In fact, there's an easy conversion. If you take 1 and divide it by the angle, the parallax angle you get in arc seconds, that equals the number of parsecs.
Right. So it makes it easy to measure.
Yeah, and it's observable, right? I mean,
yeah.
if you measure anything else like light years, right, then you got to use cosmology then, right? And that's based usually on the redshift if things are far away. So if you got the right model of the universe, you can make that conversion from what you actually measure, which is the shifting of spectral lines, to what that really means in terms of recessional velocity.
Yep.
So you got to use a model to go with that. It's not a direct observation in that sense.
So come join us and learn all this math.
The language of science.
Yes, indeed. So now we're going to show you a couple of pictures before we get into it. This is a picture of what we call an open cluster. It is an object known as designated as M38 or Messier 38. It is an open cluster. Open clusters are usually found down in the galaxy, and they are usually made up of young stars that have just formed, just blown off the nice nebula that was their nursery, and they're unstable. But they're usually made up of young stars, and they're in the galaxy.
So when you talk about our galaxy, they would be in the spiral arms. We
In
have
the
a
spiral
lot of
arms,
them,
yes.
right?
So there are exceptions, like with most things, but in general, the Pleiades, M38 here, they're all down in the spiral arms of the galaxies that they're part of. So then there's another type of stellar cluster called a globular cluster. This one is M5, our Messier object 5. There's a nice story about that, but maybe we'll get into one of these days. But this is a globular cluster, and I think you can see why we call it a globular cluster. It's a nice ball of stars. These are typically older stars. In fact, some of them are some of the oldest stellar objects that we observe in the universe. So they have different characteristics, different ways of finding out, oh, wait, maybe this is this. Nope, look at the HR diagram.
Do you remember the impact that the globular clusters had in the early 1990s related to the age of the universe?
Right. There was at least one of them that was was being aged greater than the age of the universe.
It's like you were older than your mother.
Right.
Now, how could that be? It's impossible.
There you go.
So we are finding globular clusters and using what we think were reasonable ideas in terms of their evolution, what the age of these globular clusters were. And they did not match our cosmology. The universe was younger than the oldest globular clusters.
Right.
That's a problem.
That's a problem.
And what turned out to be the solution of that, do you remember?
I honestly can't say I do. I know it was something to do with incorrect modeling of one thing or another.
It was the discovery in 1998 of dark energy. Once you threw in dark energy, you change the cosmology. It changes the age of the universe because now instead of simple expansion of the universe, you have accelerated expansion. So the time scales change. In fact, the age of the universe then came out to be older than the globular clusters.
And a lot of this plays into your error bars. I got told one time, what does that mean? All measurements have an uncertainty. And as I was told by a scientist friend of mine once, another astronomer, error bars or it didn't happen. And so a lot of times it was a matter that the error bars on these agings, these stellar models, were putting it as older than the universe. So that corrected a little bit too.
Well, it's nice to see that, when something gets proposed like dark energy, you're hesitant to accept it. You want to look at the evidence, of course, as a scientist.
Right.
But because it solves so many issues, it turns out in astrophysics, it was widely accepted a lot easier, I think, than without those sort of issues hanging around.
Right.
So when dark energy comes in, all of a sudden, a lot of things now make sense. Structural formation, the large-scale distribution of galaxies, what we call large-scale structure, the age of the universe now makes sense. Your mother is older than you.
Right.
All these sort of logical things that flow out of that. And it just, all of that together says that there must be something to this, right?
Right.
This new model
Works.
which the technical word for it is lambda, which represents dark energy, lambda CDM. So lambda CDM stands for cold dark matter. So lambda CDM means a universe which has dark energy, the lambda part, and CDM is dark matter. So it's a dark energy, dark matter dominated universe.
Right.
In fact, dark energy and dark matter makes up 95% of the whole universe in terms of mass and energy.
And a lot of people start trying to say, well, but do those things really exist? We haven't determined what they are yet and all of this. And with dark matter, the problem is we can see its effects. It's kind of like the wind. You can't see the wind, but it has effects on the items around you. Dark matter, we may not know what it is. We may not be able to see it or identify it or sense it yet, but we can see its effects through things like gravitational lensing and other such issues.
And that makes, if someone comes along and proposes that, for example, dark matter, which is the example you use, doesn't exist, then you got to come up for explanations of why you see these things that sort of indirectly point towards dark matter. Why are objects orbiting faster than they should, especially in the outer reaches of galaxies?
Right.
Why do you see the shearing and gravitational lensing effect of different galaxies spread throughout the cosmos that points to the fact that there should be dark matter? Why do galaxy clusters have all of this hot gas, and yet somehow that hot gas does not escape the cluster?
Doesn't blow away.
It's bound to the cluster because of gravity. Why do galaxies and galaxy clusters move so fast when they should violate the local speed limit? That is, they're traveling too fast given the amount of mass we see by just light coming off of stars in different galaxies. There has to be a lot more gravity to bound up those galaxies.
Right.
So whatever comes along down the road in the future, nobody knows if we got the correct model or not. We just have something that's consistent so far with all the observations. That new model will have to incorporate all of these old observations plus anything new that comes along.
Right. And that's science. So here we go. All right. So the next slide, we're going to look at some of that evolution of the open cluster and why we say they're young stars.
Right.
And this is what we call an HR diagram of 32 open clusters. This was from Gaia as well. Gaia data as well.
Data release 2. That's correct. Yeah.
So this is data of looking at the color, we call it a color diagram. And along the bottom is essentially measuring the color of the star, literally what color it is. And along the vertical axis is how bright the star is. And we call this a HR diagram. And as you can see, most of it forms a nice little line going from the upper left, to the lower right. And we call that the main sequence. These are all nice, normal stars. They're converting hydrogen into helium in their cores. And they're like our sun, in other words.
Yeah, so that's the first stage of the normal life of a star.
Right.
Once it settles down to undergo the stable nuclear fusion process of hydrogen into helium.
Yep. So high mass, really bright, really large stars are up on that upper left. And down on the lower right is dim, dark, reddish, low mass stars. So we go from O's up on the upper left, really massive stars, incredibly massive, down to the lower right, which is what we call M-class stars, and we're often referred to as red dwarfs. So what's that little tongue going off towards the upper center?
In fact, you can see the color coding on the far right, the vertical scale. That's age.
Okay.
So you take models, apply it to this HR diagram, and you can estimate the age of the different open clusters that's compiled, this composite sort of figure that you see here. So the red, if you can see the age scale, right?
Right.
Are older than the ones that have the blue color.
Right.
So the red, it'd be the older or open cluster. The blue is the younger open cluster.
And how do we get that age? Well, we apply stellar modeling, how fast the star goes through its fuel, because a more massive star, yes, it has more fuel because it has more hydrogen, but like an SUV with its big gas tank, it burns through that fuel much faster than, say, a little Honda Civic. So these big, massive stars, yeah, they have more fuel, but they burn through it a lot faster, and they last for, in some cases, less than 1 million years before they go supernova. And in the case of these M dwarfs over on the lower right, they have very little mass, so they don't have to burn much fuel to hold themselves up, and they can last for potentially billions or trillions of years.
So it's interesting to note then that the stars then don't last forever. They have a finite age.
Right.
And that includes our own sun. That might be scary until you find out the timescales. So given the present mass of our sun, we know that the total lifetime of our sun together from the moment it was born till the moment it dies is on the order of a little bit more than 10 billion years. So
Right.
including formation time in the end state. Okay. So we are roughly, from radionuclide dating of rocks on the Earth and so on, that we are roughly halfway through that total lifetime.
Right.
So we have approximately 5 to 5.5 billion years left before the sun will finish consuming the hydrogen in its core to helium. And then things will change.
Absolutely.
And that is reflected on this slide.
It is. So that little tongue jetting off towards the right is where things are moving off of the main sequence. The star has run out of hydrogen. It is now converting heat. In some cases, it is now converting helium into carbon and oxygen. And that means the core is even hotter. And a high heated gas does what? It expands. So the star swells up, it gets brighter, but it also is getting cooler because a gas that is expanding cools. Or a plasma even that is expanding cools.
Oh, you're reading the chat.
I am reading the chat. And, some of that I'm not going to get onto because it gets into speculation. But
We always read the chat. by
we
the way.
always do read the chat. But sometimes if you're asking a question, we'll try to answer it. If you're making comments, we'll a lot of times just move on. So keep that in mind. And we usually try to avoid getting into speculation about is plasma alive. Sorry, not going to go there.
Well, so the beauty in all this is that you can use the HR diagram to tell you a lot of interesting things about the evolution of stars.
Right.
In fact, historically, the HR diagram of clusters, especially globular clusters, was used to help uncover the various stages the stars go through when they're beyond the main sequence.
Right.
Its analogy here would be, for example, imagine you're a young child walking around in the forest, and you want to understand about trees and all their different life cycle that a tree goes through. So if you look at it in a forest, you'll see a large number of trees. You're going to see the standard trees standing proud.
Right.
You're going to see maybe a sapling just poking up through the bottom of the forest floor, just starting to grow from a seed. And then you'll find trees, of course, that have fallen down and are decaying. So they're dead, right? They're at the end of their lives. And so you're going to see all the various phases that trees go through in terms of their lives, the different stages.
Right.
But if you just walked along and you just see one tree in the middle of nowhere all by itself, and you had no clue about the life cycle of a tree, that one tree that you're seeing will not tell you anything about the different stages that a tree will go through.
It just tells you something about that one tree.
Yeah, you need a collection. And for example, if aliens, and I don't mean people from other country, I mean if aliens came here, people from other worlds, and they only had a fixed amount of time because they're traveling, right? So
Right.
they'll stop here for a brief moment, and they wanted to learn all they could about human activity. Where would you go? Would you go to a rural area where maybe you just see one individual, a farmer, in the field working? Or would you go to a large population center like New York City, for example? If you go to New York City, in an instant of time, let's say on 3 p.m. today, you will see places in hospitals, at nurseries where babies were just born. There could be even a mother having a baby just now. You'll see people at school milling around in the playground maybe, right, or just leaving school after the day is over. You'll see people on Wall Street running around like nuts, adults. Yep. You'll even see old age homes where people in their later part of their lives. And of course, what could happen in New York City today at 3 was that there was a funeral. And so just an instant of time, because you look at a large enough population, you can then get information about all the different life cycle that a human being goes through. And that's the same thing with stars.
And so that's what we're doing with stars. And in case you're wondering, well, don't they all look like that? Well, here's a similar diagram for a globular cluster. And you can see that bar through the middle. Well, it's number one, it's not through the middle anymore, but that straight bar going from upper left to lower right from about halfway between B and A and G.
Those are spectral types.
Those are spectral types.
And what spectral type is the sun, just so people have for reference?
Is G.
Yeah, a G2 type star.
And you can see that tongue to the right, sticking out to the right, number one, is much more populated, and it's truncated, that top left portion of the diagram. So that's why we say these are older stars, because that turnoff is happening at lower masses, and so lower mass stars, as mentioned, burn slower. They last for longer. And so we've got a lot more geriatric stars in this diagram than we did in the other.
Well, here's an example of one. Let's say you look at a cluster of stars.
Mm-hmm.
You find that the star that's at the turnoff point, right, is just leaving the main sequence now. And that star, spectral type, is a G2. It has a mass exactly equal to the sun's mass. How old is that cluster of stars?
Roughly 10 billion years.
10 billion years old. So you can use the turnoff point as a way to date the formation of the stars in the cluster.
Absolutely. So that's why we've mentioned this stuff. And that's why we're showing it to you, is because these clusters are how we date and time things.
If you find a globular cluster in which the turnoff age, given as a very, 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 very M-class low-mass star, suggests that
It's
1 trillion
years.
years has elapsed since that cluster formed, we are in big trouble in terms of our understanding of cosmology, correct?
Correct. Fortunately, such a thing has not been found.
Bingo! So for those who think the universe is not roughly 13.8 billion years old, that it's much greater, maybe 1 trillion years old, then where are all the clusters of stars that have low mass stars on the turnoff that have just consumed their hydrogen in their cores to helium, that are at 1 trillion years old? Where are all those clusters of stars? Show me one.
We would expect to see clusters of stars with those ages, and we don't see them.
Yeah, and you'd expect other ages in between those extreme values of 14 billion to 1 trillion. And you don't see any of them either. There's nothing out there.
Right.
They're not there. Why? Because the universe is not that old. That's why.
Right.
Our best estimate of the age of the universe is about 13.8 billion years old.
Right.
So if you find an object that's, 100 billion years old, then there's a problem, right? There's something wrong with our cosmology. But as we understand it today, that object wouldn't exist.
Right. So do we want to go on now to our last little tidbit for today? So there was a paper that came out from the ALMA, which is, it's an array. So
Atacama, sub-millimeter, millimeter array.
Right. So.
And it's located in Chile, up high in the Andes Mountains, which I've been. I've used telescopes, down south in the Chile and high in the Andes Mountains. A beautiful, beautiful place.
Right.
And it's located there at a very high altitude to get above most of the water vapor in our atmosphere, because water vapor likes to absorb sub-millimeter electromagnetic radiation light.
Right.
And we want to minimize that absorption. Of course, people would say, put it in space, but hand me over the money and we'll gladly put it in space.
And we'll gladly put an interferometer in space. Yeah. And we do have someone noting that magnetars last longer. Magnetars do, but magnetars are the remnants of dead stars. It has moved off the main sequence, moved through all the giant phases, and collapsed into a neutron star with a very strong magnetic field. And that's what we call a magnetar.
Yeah, there's nothing older than the age of the universe, the 13.82, nothing.
Nothing been observed yet. And if you do observe one, you won a Nobel Prize.
Yeah. And if
So-
you think that there is, and you got to have the evidence to show.
evidence.
You can't just say stuff, right?
Right.
You can't use the B word. You know what the B word
No,
is?
No.
Belief.
Belief. Right.
I believe the universe is 100 billion years old, or I believe there are objects out there that are much older than what you think the universe is. You can believe anything you want. That's up to you. But we want the evidence. This is a science.
Right.
Where's the observation? Where's the evidence? Where's the proof?
Right. And they will last longer. They're not that old yet. So, ALMA has presented that it is resolved. I'll get the words out sooner or later. The surface of a giant evolved star. So one off on that little tongue to the right on those HR diagrams.
Called an AGB star.
AGB, asymptotic giant branch.
Exactly.
So it's burning fuel other than even helium and helium. It's burning the carbon and oxygen. It's burning, heavier elements into even heavier elements. So we have this nice onion model of stellar evolution.
Yeah, and this is for a massive star. The
Massive
sun will
star.
not do this. You need
Right.
star at least 8 times the mass of the sun and beyond that value, greater than that value, for this to occur.
Right. And the bottom line is the core keeps contracting, keeps building up heat and pressure until finally iron, carbon and silicon and magnesium fuse into iron. And at that point, the star is dead. Because iron, if you fuse anything heavier than iron, you're actually having to pump energy back in. And the whole point of all this fusion is to get energy out.
Yeah, so you remember in chemistry class what those two type of reactions are?
Fission, if you're coming from the right side of the periodic
No,
table.
I was thinking something else. If something
fusion.
releases net energy, it's
Oh,
exothermic.
exothermic. Right.
And if it takes a net amount of energy for the reaction to occur, it's endothermic.
Right.
So you go from exothermic reactions to when you get to iron, and that's actually endothermic. So
Right.
it won't go. That
It won't go.
reaction.
It stops. And now you just get collapse because there's nothing left to hold it up.
And what happens during the collapse?
Kaboom. Get a shock wave as it bounces off of itself, essentially.
And the interesting thing is a lot of speculation nowadays, and I mean nowadays in the last 10 years or 20 years or so, that for really massive stars, and this is a good opportunity, Robert, to maybe invite somebody as a guest in the future to talk about massive stars, that instead of going to the supernova phase, really massive stars collapse in on themselves and immediately form
A black hole.
a black hole. No supernova, right to a black hole.
Again, never been observed, but
We've had some
stuff that
interesting
happened,
thing that's been
but-
observed that may point in that direction,
but
but nothing's been super duper verified, if you want
Right.
to use those words. You see?
so
Interesting stuff.
interesting stuff, and a real reason to come join us and learn all this math and learn all this physics and see what you can find out there. And let's see, finally, I guess on the ALMA, this is the resolve. They've deconvolved because an interferometer doesn't give you a picture like a regular telescope. What it gives you is a Fourier analysis of the wavelengths that is produced. And you can, if you have enough data from it, you can deconvolve that back into a picture. So again, a lot of math involved. And basically what it showed was that this star has convection cells near the size of a significant portion of Earth's orbit, bubbling its surface. And that's what all these bright bumps are on it.
Yeah, they're a factor about 75 times roughly the size of the sun. These convection cells, amazing when you think
This
about
is
it.
the largest star we know of, size-wise.
I mean, some of these stars get so large that if you were to take one and put it where the sun is today, it would expand out and fill the orbit of Jupiter.
Right. So, yeah, stars when they're dying are impressive.
So there are some numbers up here. The apparent size, 57 plus or minus 5 milliarc seconds.
Right. Again, all we're really measuring through a telescope is angles.
Yes.
So what that is, milliarc second, arc second again, 1/3600th of a degree. So this is 57 of those tiny units in size.
Yeah, so it's very, very tiny for sure. And the distance, 178 plus or minus 10 light years. Mm-hmm. And as Robert mentioned, this, other than the sun, This is a star that has the largest apparent size, a larger angular size as viewed from the Earth, other than the sun.
Right.
And that's a combination of how far away it is and its intrinsic size, how physically large it is.
Right.
And because it is extremely large and relatively nearby, that's why it has the largest apparent size beyond our solar system of any star.
Yeah. So great stuff.
Yeah, it's cool when you think about it.
Absolutely. I think so anyway. So, shall we conclude there? So, shall we plug our university? If you're interested in joining us, come join us. University of North Dakota offers a lot of programs online, much less in person. So, come join us. Come learn all this math. Come learn all this science. And we'll be happy to show you around or talk to you about any of the programs that you're interested in. So
now our next podcast is next Tuesday. We will have a special guest. So be prepared for that. The other thing too is we always leave a quote as the lasting thing on our podcast, and I do have one today.
Okay.
This quote, and I didn't randomly select one. I would have selected, it's from John Wayne or something. Right? What's a quote from John Wayne? Talk low, talk slow, and don't say too much, or something like that.
Something like that.
But this one is from Walter Baade, who was an astronomer from Germany, German astronomer in the 19th century. He did a lot of very important work on stellar evolution. That's why I mentioned it. And we're talking about stellar evolution today, so it makes sense why you want to bring him up. And so Walter Baade, by the way, because he was from Germany during the Second World War, he wasn't allowed to go anywhere.
Right.
And in fact, you'd probably put him in a concentration camp?
Prisoner war camp, something like that.
The story goes that his, if you like, supervisors at Caltech and so on, where he worked, allowed him or convinced the government, the U.S. government, to allow him to remain at the mountaintop in California to use the telescope during the Second World War, that he would be far removed from everything and not be a problem.
Right.
So during that time, it was a great time to use telescopes at Mount Wilson Observatory, not too far away from LA, because they would turn the lights off at night when there was a potential bomb threat. That a bombing mission is going to happen.
An air raid.
So they would take all the lights down, and all of a sudden you could see the sky without all that light pollution. And so he made some very fantastic observations of the night sky. And a lot of stuff he was looking at is the different population of stars, for example. Mm-hmm. And so he was right on the cusp, if you like, of the modern, way we know things in terms of stellar evolution. So he did some really groundbreaking work. So his quote is this: "I hope I have brought home sufficiently how little we know and how large the gaps are. In many ways, I envy those who will have to fill the gaps. I only wish that I were young and could start all over again."
I wouldn't want to start over again, but yeah, I get the point.
Given what we know now and all this technology and things that we're going to do,
I would love
let
to
me be born 200
now.
years from now and see if we're on Mars and other moons of Jupiter. Anyways, that's it for today. Thank you very much for listening.
Thanks, folks. We'll see you next week.